Hi, this is a standalone lecture. The title of today's lecture is Norms on Rn. And the main result of today's lecture will be to prove any two norms on Rn are equivalent. We will define that. Okay, this is a very most beautiful result, and it's a very nice application of the compactness of the unit sphere in Rn with Euclidean metric. And it's also a very basic fundamental result in functional analysis. So this particular lecture can be considered as part of compactness chapter in topology or the first chapter in functional analysis. So let us get started. I hope all of you already know about norms, etc. You may even know the equivalence of norms, but I'll just define that and I'll try to give you direct proof. Okay, let's get started. Yeah, so these are the references. As references, you can look at my topology of metric spaces. I have given the proof which I'm going to give in some way or other will be there, and it's also reproduced in our book on functional analysis. You also have my YouTube channel. Okay, so let us get started. So let X be a vector space over R or C also. Okay, usually algebraists will use the symbol V for vector space, but analysts and functional analysts in particular will use, and topologists will use for X, right? Any space is X for us, right? Okay, right? And what do we mean by a norm? Okay, all of you know that. So suppose I have two norms. Okay, suppose this is a one norm, this is another norm. Okay, you don't care. Sometimes some teachers use this symbol. Okay, but it will take a lot of time for me to write, so I am using a symbol P. So these are two norms where on X. Okay, and we say the two norms on X are equivalent if and only if, okay, there exist constants C1 and C2, positive constants, so that C1 times norm X is less than or equal to P times A, P of X, that is the second norm. Okay, when I write P of X, think of this as a norm. Okay, C2 of norm X. Okay, and the secret why this definition you will be explained in one of my lectures. You can also find it in my book on in the references which I had given. Okay, two norms are equivalent if and only if they induce this same topology. I don't want to stop to prove these things. Okay, perhaps I will produce another video on that. This is functional analysis do not usually explain this aspect. Remember, every norm, because of triangle inequality, it gives rise to a metric. Once I have a metric, I have the metric topology. Therefore, given the norm, there is a topology on that, on the space. Okay, therefore two norms I say are equivalent if only if they induce the same topology. Okay, so there will be a separate video where we will prove all these things. Okay, keep that in mind. Therefore, norms being equivalent is an equivalence relation. Why? Suppose this is norm is equivalent to this norm, and this norm is equivalent to another norm. Let us say this also norm on X. Right? Let this be the topology. Let this be the topology, and this be the topology. Right? Now, what I know is if these two are equal, these two topologies are same. These two are equal. These topologies are the same, and hence I say this topology and this topology are the same. That means this norm and this norm are equivalent. Okay, this is a very quick way of looking at. Also, you can use it using this inequality. This also will give rise to a proof. Okay, I don't want to stop. Okay, if you want, take it as an exercise. Prove this using the chain of inequalities, right? Okay, now what is the main result I want to prove? The main result I want to prove, okay, let P and Q be two norms on Rn, then P is equivalent to Q. Any two norms are equivalent. Okay, right? The basic idea of the proof, as I said, the proof is going to involve the compactness of the sphere. Okay, set up all x in Rn with the so-called Euclidean norm. Okay, with respect to this Rn with Euclidean norm. This is Euclidean norm equal to 1. Compactness of this. Okay, so the basic trick is, so I will prove any norm, let this be the standard Euclidean norm Rn. I will prove P is equivalent to this norm. Therefore, I will also show Q is equivalent to this norm. Any norm, right? Give me any norm P, then it's equivalent to the Euclidean norm. Therefore, it follows as P is equivalent to Euclidean norm, Q is equivalent to Euclidean norm, or Euclidean norm is equivalent to Q. Therefore, P is equivalent to Euclidean norm, that is equivalent to Q. Therefore, P is equivalent to Q. That will follow. You understand? So, enough to show if P is any norm on Rn, then P is equivalent to this, where this is the Euclidean norm. Okay, right. Do all of you accept it? Just to make sure you understand this much. Right? So that means what? I have to produce constants C1 and C2 as I have shown. Right? Let us do that. Suppose x is a vector in Rn. Okay, then I can write x as summation xi ei I equal to 1 to n. Right? Therefore, P of x will be P of this summation xi ei, but that will be less than or equal to by triangle inequality, or maybe let us do that. This is, yeah, are you following? This will be equal to P of x I equal to 1 to n. Right? This is by triangle inequality. But remember, xi's are scalars, maybe complex scalars or real scalars. Therefore, this is equal to mod xi times P of ei, I equal to 1 to n. Right? But notice that mod xi is less than or equal to the Euclidean norm x. See, this is one of the places where we are using our norm is Euclidean norm. You understand? If you have given me an x and write it as summation xi ei, I may not know whether there is any relation between mod xi and P of xi. Sorry, P of x. I do not know. Okay, but in the Euclidean case I know, because what is this? I know that Euclidean thing, this is summation mod xi squared 1 to n. Right? Therefore, mod xi squared is less than or equal to this, and hence mod xi is less than or equal to norm of x. Do you follow that? So this is one place where we are using a special norm. Okay, keep that in mind. Right? Therefore, what do I have? P of x. So this one, okay, this one now reduces to P of x is less than or equal to, I am just writing it again, norm of x into P of ei. Right? So there are many ways of doing. For example, you can, this is less than or equal to P of ei times norm of x. So call this a C, C1 or C2 or whatever, I don't care. Okay, let's say C2. Have you understood this? Why I can do? Remember, where I am using the fact this sum is finite. How do I know the sum is finite? Because I am dealing with only Rn. Do you see that? This is a subtlety. Okay, so two things we had already used. What did we use? Our special choice of Euclidean norm ensured this happens. And second thing, okay, this sum is finite. That's because the sum itself is a finite sum, and hence the sum exists. Call it C2. It's a non-negative. It's right. Third, why C2 is positive? Because remember, EI is not zero, P is a norm. Therefore, P of VI is not zero for any I, right? Therefore, it's actually positive. For each I, P of VI is positive. Therefore, this is a positive sum. Have you understood? So, we have shown there exists C2 positive, so that for all x in Rn, okay, P of x is less than or equal to C2 times norm of x. Pause, review, proceed. Now there is something very interesting happening. See, it's okay. So let us have a digression. Okay, suppose X is a non-linear space. Okay, X need not be Rn. Yeah, it's a vector space over R with a norm. Right. Then I can consider this norm as a function from X to R. Okay, remember this is a non-linear space, therefore there is a metric and hence there is a topology. This function is continuous with respect to that topology, with respect to the norm topology. That is with respect to the norm itself, because norm is, it gives rise to a metric, right, with respect to the metric. This is the usual thing. Yeah, how do I prove that? You start with any point x0 in X, then I have to say norm of x minus norm of x0. I have to estimate modulus of this, but this will be less than or equal to norm of x minus x0, right? So if I want to show this is less than epsilon, I can choose delta to be less than epsilon, therefore this will happen. Are you following? You give an epsilon, call this if you want f. So I want to show f is continuous at x0. That means what? I have to prove this is less than epsilon whenever distance between x and x0 is less than delta. But that is norm of x minus x0 is less than delta. Okay, should imply that. But what is fx? That is norm x. What is fx0? Norm of x0 and absolute value. But this is the, okay, triangular inequality. Okay, so let me just quickly go through this, why this is true. Why this is true? Remember, for every xy in a non-linear space, okay, modulus of norm x minus norm y is less than or equal to norm of x minus y. Okay, the reason is I can write norm x equal to norm of x minus y plus y. Therefore, treat as, use the triangular inequality, is norm of x minus y plus norm y. Okay, bring norm y to this side. Okay, now interchange x and y. But these are equal. Okay, so this shows modulus of norm x minus norm y, which is the maximum of norm x minus norm y, or minus of norm x minus norm y. Okay, but each one of them is less than or equal to norm of x minus y. Therefore, is proved. I'm sure all of you must have seen, but in case some of you, because this is one thing which I keep saying, whenever some small such things come, small items, small facts, what I do is I quickly mentally go through the proof. Okay, here I, instead of mentally going through, I give the proof to you. You should also make it a practice so that you will become confident. Okay, It is the same trick you used learning multiplication table. In the beginning, you memorize the multiplication tables, but you keep on doing lot of multiplication, then without quoting the multiplication table, you will immediately give the answer. 7 times 8, 9 times 4, 3 times 8. All such things will come out quickly. The same trick. Anyway, come back. Okay. So remember, let's go back to Rn with the Euclidean norm and the thing. What I proved? P of x is less than or equal to C2 times norm of x. C2 times, norm of x. For all x in Rn. There exists C2 positive, so that is happened. Yeah. And this is something interesting. So see the map here, x going to P of x, this is continuous with respect to the P norm, right? That's what I proved. On any non-linear space, the norm function is continuous. Therefore, in the norm space Rn comma P, x going to P of x is the norm function. That is continuous with respect to what topology? With respect to the norm P norm. But what we have proved is something very interesting. Okay, this one, let me put it as a different color. This one says something more. It says the map P map from Rn with the Euclidean topology, Euclidean norm to R is continuous. Something fantastic. Okay, very subtle and significant. How do I prove that? Again, do that. So fix an x in Rn. I want to prove continuity of P at x. What does that mean? That means you give me a y, then I would look at Py minus Px, and it's a real value, therefore distance between them, I want to say, is less than epsilon. Right? But just now what I did, but for any norm we said that, let's go back, for any norm we proved this result, modulus of norm x minus norm y is less than norm of x minus y. Now our norm is P, right? Therefore this is less than or equal to P of y minus x, right? But then remember, because of this the inequality we have proved, right? Because of star, what do we get is this less than or equal to C2 times Euclidean norm of x minus y or y minus x, right? So when I wanted this to be less than epsilon, it's enough if we make sure this is less than epsilon. That means I have to choose a delta which is positive, such that is less than or equal to epsilon by C2. Right? So please again go through. So what we proved is the P norm on Rn, but with respect to the spaces with the Euclidean norm to R, x going to Px is continuous. In fact, we showed it's uniformly continuous or Lipschitz continuous, etc. But important thing is continuous. Okay, pause, review, proceed. Now what is that I have to prove? I have to prove there is a C1. Okay, to prove the other way around, I want to know whether there is a C1, so that C1 times norm x is less than or equal to P of x for all x in Rn. Okay, to prove this, right? Let's look at that. Means for all x in Rn, I should have P of x is greater than or equal to C1 times norm of x, right? And this is the Euclidean norm, right? So this is the next trick. So remember, because of homogeneity, P of Tx, if T is positive, it's same as T times P of x, right? So it's enough if we prove this for unit norm, for unit vector. Why? That is, I have to prove for every unit vector, that is norm of u equal to 1 in Rn with this norm. Okay, that is greater than or equal to C1. Why? Because if you give any x non-zero in Rn, then let's look at u equal to x by norm x. Then norm of u will be 1. Therefore, what will I have? Therefore, I know P of u is greater than or equal to C1. That will imply P of x by norm x is greater than or equal to C1. Right? But 1 by norm x is a positive constant. P is a norm. Therefore, this means 1 by norm x times P of x is greater than or equal to C1. That means P of x is greater than or equal to C1 times norm x. So I have proved the result, right? Have you understood? Pause, review, proceed. Right? Now let's look at yes, the subset of all x in Rn with Euclidean norm of x equal to 1. This is the set of unit vectors in Rn with the Euclidean norm. Right? So what do I know about this set? I know this set is closed and bounded. Why it's closed? X going to norm x from Rn with this norm to R. This is a continuous function, right? Therefore, yes, s equal to, call this as continuous function. Okay, this norm function. Therefore, s is this function inverse of singleton 1. Do you follow this? This I am considering as a function now. Therefore, its inverse image of the singleton 1. Singleton 1 is closed. Therefore, this is closed. Why it's bounded? Of course, for every vector in S, its norm is 1. Therefore, it's bounded, right? And hence, by Heine-Borel theorem, S is compact subset of Rn with Euclidean norm. Okay, very good. Now let's look at what you have done. So now I have function P, which is from Rn to R, x going to P of x, Rn to this norm. I know this is continuous. Therefore, restriction of P to S is also continuous. Right? Therefore, the function P from S to R, any unit vector going to P of u. P of u may not be 1. Okay? This is continuous. Right? Now, what do I know about S? S is compact and P is a real valued continuous function. Therefore, what do I know? What is the important result about this? Okay? So, there exists a unique, there exists a vector, an element, call it as, if you want, u0 in S, so that P of u0 is the minimum. Yeah, right? P of u0 is the minimum. What does it mean? For every u in S, P of u is greater than or equal to P of u0. Do you understand this? Right? That's because of the wonderful fact that P, the norm function P from Rn with Euclidean norm is continuous. That fact we used, and the compactness of S. Right? Now what did we say? I only have to say there exists a C so that for every unit vector in Rn with Euclidean norm, P of u is greater than or equal to C1. Now what I have done is P of u is greater than or equal to P of u0. So what is that I have to do? If I would like to take C1 equal to P of u0, but then I have to ensure this is whether is positive. Right? Remember, P is a norm function, therefore P of u0 is always greater than or equal to 0. Can it be 0? P of u0 is 0. Remember, u0 is P is a norm. That will mean u0 is 0. But u0 is a vector and its unit vector. Therefore, its Euclidean norm should also be 0. because u0 is a zero vector. Therefore every norm of the zero vector must be 0, but that I know with respect to Euclidean norm it's 1. This is a contradiction. Therefore what I have concluded? I have concluded if I take C1 equal to P of u0, it is positive. Therefore what I have shown? For every u in Rn with Euclidean norm equal to 1, P of u is greater than or equal to C1. Right? Therefore if you give me any non-zero vector, then as usual applying by x by norm x, that will be greater than or equal to C1, or P of x will be greater than or equal to C1 times norm x. This is for every non-zero vector. If the vector x is 0, notice that again the result is true, because P of x will be 0, norm of x will be 0, therefore 0 is greater than or equal to C1 times 0. That's a correct statement. Right? So what do you think I have proved? So I have proved there is a C1 and C2, so that C1 of norm x is less than or equal to P of x, that's less than or equal to C2 of norm x. So in other words, I have shown both the norms, the given norm is equivalent to, the given norm P is equivalent to the Euclidean norm, and hence any two norms on Rn are equivalent. Go through the proof. I somehow like this proof, love this proof. Right? There are a lot of subtleties. You see that? First we restrict, instead of any two P and Q, we show that P is equivalent to Euclidean norm is good enough. Okay. Second thing, what did you observe? Because of using finite dimensionality, we said P of x is less than or equal to some constant times Euclidean norm of x, where we used finite dimensionality. The third observation is this inequality actually showed the norm map P from Rn with Euclidean norm to R is continuous. Okay, the fourth fact we need is we restricted this function to the compact set S, which is the set of unit norms with respect to the Euclidean norm. And we know by highly probability it's compact, therefore my norm function P will attain a minimum. That's it. Isn't it a beautiful proof? I hope you enjoyed it. Okay, we'll meet again.